electric safety, danger, electrocution risk. So the electric current may be dangerous to human beings and installations. The human body conducts electricity, and the passage of an electric current more than 30 milliampere may lead to severe muscular contraction that may cause death. This is called electrocution. In this chapter, you're going to learn how to protect yourself from electrocution and how to protect electric appliances and installations. So the objectives are to protect ourselves and to know how to protect electric installations, vocabulary terms, short circuit, grounding, circuit breaker, fuse, and electrocution. Starting with the protection of individuals. The fact is that in a wet medium, an electric voltage higher than 25 volts sends a current more than 30 milliampere through an individual. However, in a dry medium, an electric voltage higher than 50 volts sends a current more than 30 milliampere. And aside here we have a table that shows the effect of each intensity of current on the human or on an individual. 0.5 milliampere causes nothing. 7 milliampere is a little bit painful. 15 milliampere causes muscular contraction. 30 milliampere causes loss of muscle control. 100 milliampere suffocation, difficulty in breathing, and greater than 100 milliampere causes the heart to stop and thus causes death. So knowing that in Lebanon the household electricity has a voltage of 220 volts, yani the voltage provided by the wall outlets at your homes is 220 volts, which is much greater than the limit whether in dry medium or in wet medium. So it is really dangerous to get electrocuted by the voltage of the household electricity. So here you have two links for two videos to watch on YouTube. They are helpful. You can watch them. Now, starting type. We said that 50 volt and 25 volts are dangerous voltages. So how can we protect ourselves? We have to know that the wall outlet at home must have three terminals: neutral, hot, which is the live, and the ground. So as you can see here, the live line carries the current to the wall outlet, and the neutral carries it away. However, the earth line in normal cases doesn't carry any current. Okay? So what happens, or what's the importance of the earth line, or when does it function? It is when, for example, here, suppose there is no ground. Some wall outlets that do not have a grounding or are not connected to earth lines. So suppose that the red insulator of the wire is damaged and the wire is in contact with the metallic body of the washing machine. So now the red insulator, this represents the live line. So the live line is carrying the current to the cover of the metallic body of the washing machine. Would the user of the machine be electrocuted if she touches it? Yes, for sure, because touching it, she is a very good conductor. So as if she is in direct contact with the live and standing on the ground. So there is a complete circuit here. The current will pass from the live line to the cover, to the metallic part of the washing machine, through the individual's body to the ground. So yes, she will get electrocuted. So why? Because the current will pass from the live line to the metallic part of the washing machine and then go to the ground through the woman. However, if the wall outlet had a grounding line in which this line is connected to the ground and to the washing machine, the wall plug now is grounded. This yellow or green is usually insulated with a yellow or green insulator. The live red wire is in contact with the body of the machine. The user touches the machine but does not risk electrocution. Why? Because when there is leakage of current from the live line to the metallic body, the earth line detects this leakage and thus opens the way for the current to pass through it into the ground instead of passing through the woman. Okay, so what's the role of the grounding? Grounding ensures here protection from electrocution. Now, protection of installations. If we consider now a simple circuit as shown in the adjacent figure, the dry cell provides a current in the circuit so the lamp brightens normally. So we have a battery connected to a lamp by two wires. Now, if we, for example, connect the two terminals of an element of a circuit with a connecting wire. As you can see here, we're connecting the two terminals of the lamps to each other, of the lamp to each other. So we say that a short circuit is formed. What do we mean by a short circuit? Here we can consider that there's short circuit on the lamp and on the battery, because also the wires connecting the two terminals of the battery from this side and from this side, they're connected to each other by a wire. So does the dry cell provide a current? Yes, it still provides a current because we have a complete closed circuit here. The where does the current pass? Through the short circuit. Why do I consider it to be a short circuit? So as you can see, the lamp doesn't glow because no current is passing through it. However, the current is passing through the short circuit. Why do we call it a short circuit? Because the wire has no resistance. So the current finds it easier to pass through the wire instead of passing through the lamp that has resistance. Okay, so it passes through the wire and back to the battery. But does the dry cell become warm? Yes, since the current is of high intensity. As long as the current is passing through a pathway that doesn't have resistance, so now it has a high, it's high in intensity because the voltage of the battery is high and there is no resistance, so a high current will be driven through the short circuit, and this may cause fire. Okay, here also consider the circuit of figure 3a. Two lamps are grouped in series. Between the two poles of a dry cell, the circuit is closed. The two lamps light up normally. As you can see, these are dry cells connected to two lamps in a closed circuit. Connect to the lamp a short circuit to one of the lamps. A short circuit, this means that connecting the two terminals of the same lamp to each other by a wire. Does the other lamp light up normally? Yes, because the current will come out through this pathway, through the short circuit, and continue through the other lamp. So it will glow, but it will glow strongly. Okay, so the other lamp now is glowing strongly. Why? Because the cell is providing a larger current. So does the cell provide a larger current? Yes, the cell provides a larger current. Because upon short-circuiting this lamp, it's as if it's excluded from the circuit, and now the current is passing through this part that doesn't have resistance. So the resistance in the circuit decreases, and thus the current increases. Now, if we remove the short circuit, do the two lamps light up normally? Yes, the lamps glow normally. Again, if this lamp was not burnt out, so they will again function normally if we remove the short circuit. So what can we deduce concerning the short circuit? The short circuit of an electric component in series grouping causes an increase in the main current. Similarly, here if we have parallel grouping, you can see here a battery, an emitter connected in series to the battery to measure the main current, and two lamps are connected in parallel. وفي هون the third branch that includes an open switch, so as if it's not present so far. What is the main current of this parallel grouping? It's 1.8 ampere. However, if I close this switch here, now switch acts like a connecting wire. So here, as if I'm connecting the terminals of this lamp by connecting wire. Also, the terminals of all the components are considered to be connected to each other by this wire because they are parallel. So here we have a short circuit too. The current will no more pass through the two lamps. Instead, it will pass through the short circuit, and it will be very high. So this may cause fire. The battery gets warm and may cause fire. Okay, so similarly in parallel grouping, the short circuit of an electric component causes an increase in the main current. Now, what are the two ways to protect installations in case a short circuit took place or overload was taking place? So during a short circuit at home, an intense current passes in the conductor and becomes excessively hot. If the house is not protected from short circuits, this may cause dangerous fires. So what devices may be used to protect the electric appliances and installations? They are the circuit breaker and the fuse. A circuit breaker carries an indication on it. So we read the indications 40 ampere on the circuit breaker, which is put at the output of the electricity meter. What does the indication represent? It represents the maximum current that the circuit breaker allows to flow through it. So in the case of a short circuit, when we use many devices at the same time, the value of the current surpasses the current indicated on the circuit breaker. So what's the role of the circuit breaker in this case? The circuit breaker cuts off the circuit, preventing the flow of high current that may cause fire. So does the circuit breaker protect the electric installation? Yes, the circuit breaker protects the installation from fire. And to explain the idea here, let's represent the installations at home. They are connected in parallel. Suppose that this is the main source. Okay, this is the main source, and we have here a circuit breaker that carries an indication of 40 ampere, or let it be smaller, 10 ampere. Suppose that. Okay, so it maximum allows 10 ampere to pass through it. Now this is the main source. Okay, now if I turn on refrigerator, for example, here I main is coming out of the main source, passing through I1. Okay, so now I main is only equal to I1. I have only the refrigerator turned on. Okay, I main is equal to I1. If we turn on, for example, the washing machine now, they're connected in parallel at home, the current will pass through the washing machine, and now I main is equal I1 plus I2 due to the law of addition of current in parallel grouping. So the main current will increase, and so on. If we keep on turning on more and more devices, for example, if I turn on now the TV, okay, in parallel, we will have I3 through this branch, and I main will be equal I1 plus I2 plus I3, and so on. Okay, suppose that we keep on turning on more and more devices until the main current exceeds 10 ampere. So the main current, the circuit breaker here will directly indicate that a current more than 10 ampere is tending to come out of the source. So it cuts off the circuit. It opens. That's now like an open switch, preventing high intensity current from passing through the installations, because the high intensity current here may cause fire. The wires may not bear this high intensity current. Okay, so we have to remove some appliances. For example, we turn off some appliances and then turn on the circuit breaker. The circuit breaker doesn't burn out, it only cuts off the circuit. It acts like a switch, and then we turn it on again, and the other devices will function normally. Now for the fuse, is a safety device consisting of strip of wire that melts and breaks an electric circuit if the current exceeds the value indicated on it. So we have different fuses: 3 ampere, 5 ampere, 13 ampere. This allows only 3 ampere to pass through it. This allows 5 ampere. This allows 13 ampere. So suppose that the lamp carries an indication of 3 ampere on it. So this means that it functions normally when 3 ampere passes through it. So we have to connect a fuse that also allows only maximum current of 3 ampere to pass through it. Okay. By the way, the voltage of in here, the fuse acts like a connecting wire. It doesn't take voltage, it only allows the passage of current. But if the current passing through it exceeds the indication on it, it cuts off, it melts and cuts off the circuit. So suppose a high voltage battery is connected to the lamp, and a current of 4 ampere, for example, is driven through the circuit. This 3 ampere fuse will indicate this high current and cut off the circuit, protecting the lamp from being traversed by high intensity current. So the fuse should be connected in series to the device that it is protecting, in order so that when it cuts off, the current is cut off and the electric component is protected. So in conclusion, a voltage higher than 25 volt may cause electrocution. A short circuit increases the current in the circuit, thus overheating the conductors and may cause fire. And the ground, the fuse, and the circuit breaker are used to protect human beings and electric appliances from installations. So here we have some precautions that we have to take into consideration. We have to avoid short circuit. We have to use plug covers so that babies do not insert conductors in the live terminal of the wall outlet and get electrocuted. We have to watch for bare cords. We have to make sure that all the cords are insulated. We should not repair equipment when they are plugged in the wall outlet. We should disconnect or turn off the lamp before we fix it, and we should not plug many devices on the same wall outlet.